A topic that really spans everything. From the incredibly vast to the infinitesimally small, we're talking about the bounded and unbounded nature of photon energy. From cosmological scales to the Planck limit. Basically, this deep dive is all about unpacking one of physics' most elegant equations, EPFF, and exploring its frankly mind-boggling physical limits.
That's right. And our mission here isn't just to, look at EKF as a piece of math, because mathematically, sure, energy could be anything from zero right up to infinity. Instead, we're digging into the physical principles, the things that actually set the ultimate boundaries for a photon's energy. It's a journey from abstract math to, well, physical reality, how the cosmos sets a floor and quantum gravity sets a ceiling.
Exactly. And for this journey, we've gathered some fantastic sources. They give a really comprehensive analysis looking at both the minimum and the maximum possible energy a photon can have. So let's get into it. EHF, it looks so simple on paper, doesn't it? But what's really staggering is how this tiny equation just fundamentally shifted everything. It took us from classical physics, where energy was always smooth, continuous, to a world where energy deep down comes in packets, discrete chunks. Okay, let's unpack this. How did such a simple formula revolutionize our whole understanding of light?
It's a great story, actually, and it starts with a struggle. Go back to 1900. Max Planck is wrestling with this problem called black-body radiation. Classical physics, it just failed spectacularly. It predicted that a hot object should emit infinite energy at high frequencies, which is obviously wrong. They called it the ultraviolet catastrophe.
Right, infinite energy makes no sense.
Exactly. So Planck, in what he later called an act of desperation, he proposed something radical. Maybe energy isn't continuous. Maybe it's emitted in these discrete packets, these quanta, and the energy of each quantum was proportional to frequency. But, he initially saw it as just a mathematical trick, something to make the equations work, not necessarily a fundamental truth about energy itself.
So Planck thought it was just a calculational fix, a workaround. And that's where Albert Einstein steps in 1905, right? He looked at Planck's idea and applied it to the photoelectric effect, where light hitting metal kicks out electrons. How did Einstein connect those dots? How did he see this deeper physical reality?
Einstein basically said, well, if energy is quantized when it's emitted or absorbed by oscillators in matter, then maybe light itself, when it interacts, is also made of these quantas. He argued light travels in these discrete packets, light quanta, we now call them photons, each carrying energy E off tau. And this idea perfectly explained the photoelectric effect puzzles.
Like why the electron energy depends on the light's color, its frequency.
Exactly. And not on how bright the light is, its intensity. And it explained the threshold frequency, why you need certain minimum frequency to kick out any electrons at all, no matter how intense the light. It was a really profound insight.
A true paradigm shift, wow. And then Robert Millikan's experiments, they confirmed it with incredible precision, right? That really cemented the photon as a real thing and got Einstein his Nobel Prize in 21.
Precisely. It wasn't just a math trick anymore. It was physics. And EAGS became, you could say, the core expression of wave-particle duality. It links a particle property, this discrete energy packet, directly to a wave property frequency. Then Lee de Broglie took it even further, suggesting that particles like electrons also have wave properties. It showed Planck's constant AH is truly universal.
What's so fascinating, though, is that purely mathematically, EHF is just linear, unbounded. Energy could be zero, it could be infinite, no limits in the math itself. And that, for me, is the real tension here, this contrast between the abstract math and the constrained physical world. And what defines these incredible real-world limits we're exploring? It comes down to the universe itself, its size, extreme gravity, but also these fundamental constants. Things like H, Planck's constant, C, the speed of light, G, the gravitational constant. And many of these aren't just measured anymore, they're defined exactly. They're the bedrock. So using these constants, how do we figure out the absolute lowest energy a photon can possibly have?
Okay, that takes us to the cosmological scale. It's a theoretical limit. Remember E-chi. So minimum energy means maximum wavelength. What's the biggest box you could put a photon in?
The universe.
Exactly. The observable universe. And you have to account for its expansion. Right now, its diameter is estimated at about 93 billion light years. That's roughly 8.8 times 10 to the 26 meters. If you plug that huge distance in as the maximum possible wavelength,
You get a minimum energy.
you get a theoretical minimum energy. It comes out incredibly small, around 1.4 times 10 to the minus 32 electron volts.
Wow. 10 to the minus 32. That's almost impossible to even imagine. So a photon with basically zero energy is one that's just stretched across the entire visible cosmos.
That's the idea. And what's really cool is that this limit isn't fixed. As the universe expands, this maximum wavelength gets bigger, so the minimum energy gets smaller. It keeps decreasing, heading towards zero. So the energy source for a single quantum particle is tied to the history and scale of the entire universe.
That connection is just mind-blowing. But okay, how on earth do you even try to detect something with energy that low? I mean, we detect really low-frequency radio waves, like ELF waves, classically. But a single photon down there, that sounds almost impossible. Is that a fundamental barrier or just a tech challenge?
That's a great question. And thankfully, it seems to be primarily a technological hurdle. We're not hitting a wall where physics breaks down. It's just incredibly hard to pick out such a tiny energy packet from all the background noise, the thermal static. But the experimental frontier has made some amazing progress.
Like what?
Well, think about the cosmic microwave background photons, the CMB, the oldest light there is. Their peak energy is around 7 times 10^4 eV. We detect those all the time, though usually as a collective glow, not individual photons. But recently, using superconducting detectors, scientists have pushed single photon detection way down into radio frequencies. There have been detections at 5 gigahertz, then 200 megahertz. And the record, I believe, is a single photon detected at 173 megahertz.
Okay, 173 megahertz. What energy is that?
That corresponds to about 7.15 times 10 to the 7
Okay.
electron volts.
Right, so 10^7 eV detected. The theoretical limit is 1032 eV. That's still a vast chasm, as you said, like 25 orders of magnitude difference. It really shows the scale of the challenge.
Okay, let's play devil's advocate. What if there was some fundamental non-zero minimum energy? Forget the cosmological limit for a second. What if a photon just couldn't exist below, say, 1040 eV? What would that imply? Oh, the consequences would be huge. Really catastrophic for current physics. First off, it would almost certainly violate Lorentz invariance. That's the bedrock of special relativity.
Right.
Why? Because of the Doppler effect. An observer could just accelerate to a different reference frame and redshift the photon's energy down below that hypothetical minimum. That's a paradox. The only way out is if Lorentz invariance isn't perfectly exact.
Which would rewrite a lot of physics.
A lot. And it gets worse. A non-zero minimum energy strongly suggests the photon would have to have a tiny, non-zero rest mass. If photons had mass, even a tiny bit, they wouldn't travel at the speed of light, to see. And electromagnetic forces wouldn't have infinite range anymore. They become short range, like the weak nuclear force. Maxwell's equations would need changing, probably to something called the Prokik equations. It changes everything from atoms to cosmology.
But we have tests for photon mass.
Right. Extremely good ones. Experiments have put incredibly tight upper bounds on any possible photon mass. We're talking limits like less than 1018 electron volts for the mass equivalent, even down to maybe 1027 eV in some analyses. So all the evidence, both theoretical consistency and these super stringent experimental limits, points very strongly to the photon being truly massless, which means its theoretical minimum energy is exactly zero. The only effective floor is the one set dynamically by the size of the universe.
Fascinating. Okay, so the floor is zero, practically set by the cosmos. Let's flip it. Let's go to the other end. The maximum energy. What's the absolute ceiling? Feels like we're shifting from the vastness of space to something extreme and maybe tiny.
That's a good way to put it. And like the lower bound, there's sort of two limits to consider. First, there's a practical observational limit. The universe itself isn't perfectly transparent to extremely high-energy photons. It becomes opaque.
How does that work?
It's a bit like the GZK limit you might have heard of for ultra-high-energy protons. Those protons interact with the cosmic microwave background, lose energy. Well, ultra-high-energy photons also interact with background light, both the CMB and the lower-energy extragalactic background light, the EBL. The main process is pair production. The photon hits a background photon and creates an electron-positron pair, G plus E, EOE plus E.
Ah, so the high-energy photon gets destroyed, essentially.
It gets absorbed, its energy converted. And this process is energy-dependent. The higher the photon's energy, the more likely it is to interact, and the shorter the distance it can travel before doing so. This creates an effective horizon. We simply can't see photons above a certain energy, roughly in the PV range, that's 1015 eV, or maybe high TV, 1012 eV, if they come from very distant sources. The universe filters them out.
So that's the observational ceiling. But theoretically, could a photon have even more energy if it was created nearby, or if we ignore that absorption? I've heard this wild idea. Can a photon get so energetic it collapses into its own black hole? Is that the ultimate limit?
You're right on track. That is indeed the ultimate theoretical limit, and it's tied to something called the Planck energy. This is derived purely from fundamental constants. C, speed of light, reduced Planck constant, and G, gravitational constant. It works out to be an absolutely enormous energy, about 1.22 times 128 electron volts. That's 10 to the 19 billion electron volts.
Okay, 1028 eV. What's the significance of that energy scale?
It's the energy scale where we expect our current theories, quantum mechanics and general relativity, to basically merge or break down.
Right.
It's where quantum effects and gravitational effects become equally important for a single particle. Gravity becomes strong, even at the quantum level.
Right. So how does the black hole idea fit in? How can a photon, which has no mass, form a black hole?
It's a fascinating thought experiment based on ETC12, or really EPC plus MC spatial. Even though a photon's rest mass, m is 0, it has momentum, p, and therefore energy, EPTT. And energy, according to general relativity, warps space-time just like mass does. So you have this interplay between two fundamental length scales associated with the photon, which are, first, its Compton wavelength, FHP equals HCE. You can think of this as its quantum mechanical size, the region it's localized in. As the photon's energy E goes up, its Compton wavelength gets smaller. It becomes more point-like. Second, you have its Schwarzschild radius, RS equals 2G Esho. This is the radius of the event horizon it would create if its energy E were concentrated enough. As the photon's energy E goes up, its Schwarzschild radius gets bigger. Its gravitational influence increases.
Ah, I see. One shrinks, the other grows as energy increases.
Exactly. And the ultimate theoretical limit occurs when these two scales become equal. The point where the photon's quantum localization size, Compton wavelength, shrinks down to the size of its own gravitational trap, Schwarzschild radius. At that moment, the energy is so concentrated in such a small space that it inevitably creates a tiny black hole. The photon is trapped within its own event horizon. It ceases to exist as a freely propagating photon.
And that happens at?
That happens at an energy scale, numerically, on the order of the Planck energy we just mentioned. And the corresponding length scale is the Planck length, about 1.6 times 1035 meters. The smallest distance that seems to have physical meaning in our current understanding.
Wow. So the absolute maximum energy is set by the point where quantum mechanics and gravity essentially force the photon to collapse on itself. What's just incredible here is the total dynamic range, from that cosmological floor of maybe 1032 eV to the Planck ceiling around 1028 eV. That's
60 orders of magnitude.
60. It's just staggering. It really highlights the photon's unique role as this messenger particle that connects literally all physical scales.
It really does. And it points to what you might call a duality of limits, a kind of cosmic symmetry. Think about it. The minimum energy, the longest wavelength, is effectively set by the biggest thing we know that's size of the observable universe. While the maximum energy, the shortest wavelength, is set by the smallest meaningful scale, the Planck length, where quantum uncertainty meets gravitational collapse.
So the particle's properties are bounded by the universe at its absolute largest and smallest extremes.
Precisely. It suggests this deep, almost holographic connection where the properties of a single quantum entity are defined by the global structure of the cosmos.
That's a really profound way to frame it. And thinking about these limits, it naturally leads to, well, what's next? What are the big questions, the avenues for future research here? Where are the frontiers?
Absolutely. There are exciting frontiers at both ends. At the low-energy frontier, there's that huge 25 order of magnitude gap between theory and experiment we talked about. Pushing detection limits down into the megahertz, kilohertz range, or even lower requires completely novel detector technologies, probably building on those superconducting devices. Success there could be revolutionary. It might let us see signals from the cosmic dark ages before the first stars formed, signals redshifted down to incredibly low energies. Or it could provide brand new ways to test fundamental physics search for tiny photon masses, look for subtle violations of Lorentz invariance in a completely unexplored regime.
Okay, so huge potential discovery space down low. What about up high, the high energy frontier?
That's the GZK region and beyond. While we see the energy cutoff, there are still puzzles. Different experiments sometimes get slightly different results about the exact energy spectrum, and crucially, what kind of particles make it through at the highest energies? Are they protons, heavier nuclei? We need next-generation cosmic ray observatories, bigger and more precise, to really pin this down. And who knows, maybe in that extreme energy regime, we'll find subtle hints of physics beyond the standard model. Perhaps signatures of decaying super-heavy dark matter particles, or, again, maybe faint signs of Lorentz invariance breaking down only at very high energies.
And then there's the ultimate frontier, quantum gravity, and the Planck scale itself. How do we possibly probe that? We can't build a Planck energy accelerator.
No, we certainly can't. Direct tests are out of reach for the foreseeable future, probably forever. But the key is indirect probes. Whatever the correct theory of quantum gravity turns out to be, string theory, loop quantum gravity, something else that likely operated in the very early universe. And it might have left faint, subtle imprints on the largest scales we observe today. So, by making incredibly precise measurements of the cosmic microwave background, mapping the distribution of galaxies across billions of light years, searching for primordial gravitational waves, we might be able to see those subtle signatures, those echoes of Planck-scale physics from the universe's birth. It's looking for tiny clues in vast amounts of cosmological data.
What an incredible journey that was. From the edge of the observable universe defining the lowest energy all the way up to quantum gravity setting the ultimate ceiling. It really puts the photon's role in perspective.
It does. And maybe it leaves you with a final thought to ponder. How might the very structure of our universe, its expansion, its fundamental constants, and the limits of its smallest possible scales ultimately define the quantum nature of absolutely everything within it? Are the properties of particles, like photons, echoes of the cosmos itself?
A truly fascinating question, something for all of us to think about. Remember, your deep dive into this incredible topic has only just begun.